Welcome to this explainer. If you've been wondering why extreme weather just absolutely dominates the headlines year after year, well, the answer is actually lurking right beneath the waves. Today, we're diving into the fascinating, yet pretty sobering, science of how our warming oceans have transformed from a moderating force into an overcharged battery, one that's actively fueling some of the most extreme storms we've ever recorded. It is a brilliant and, frankly, wild look at planetary physics in action. To wrap our heads around this massive shift, we're going to follow a quick roadmap today. We'll start by uncovering the ocean's hidden heat, look at how that actually fuels these monster storms, clear up the difference between surges and tsunamis, check out the real-world human and ecological toll, and finally, talk about how we can prepare for what's coming.
All right, part one, the ocean's hidden heat, or what I like to call the overcharged battery.
90%. It is just staggering to think about, but our oceans absorb over 90% of the excess heat generated by greenhouse gas emissions. You got to think of the ocean as this colossal heat reservoir, basically a massive global sponge. When human activities, mostly burning fossil fuels, pump greenhouse gases into the atmosphere, all that trapped heat doesn't just hang out in the air. The vast majority of it gets locked straight into our oceans.
For the longest time, the ocean actually moderated our land temperatures. It was our planetary shield, keeping the climate nice and stable for human development. But with this insane, rapid accumulation of heat, we really have to ask a serious question. What happens when that battery gets completely overcharged? When exactly does our shield turn into a ticking time bomb? Because frankly, all that massive energy has to go somewhere.
And looking at the recent data compared to our historical baseline, wow, a profound shift emerges. In 2025, global oceans hit their highest recorded heat content ever, sitting a full ½ degree Celsius above that historical average. Now, ½ degree, that might sound tiny if we're just talking about the weather outside your window, but apply that ½ degree across the immense volume of the entire world's oceans, we are talking about an absolutely unfathomable amount of stored thermal energy.
And here's the really scary part. The danger isn't just sitting on the surface. This human-driven warming is penetrating incredibly deep into the water column. We're talking about enormous heat accumulation, pushed all the way down into the upper 2,000 meters of the ocean. So this creates a massive three-dimensional reservoir of energy. It's not just some warm layer on top. It's a deep, deep well of heat.
Which brings us to part two, fueling monster storms, the engine of destruction. To really understand the engine driving a tropical cyclone, or a hurricane, or a typhoon, we have to talk about its fuel, and that fuel is latent heat. Basically, this is the energy transferred when water changes state. So when you have unusually warm sea surface temperatures, that water evaporates into the air way more readily. As it does, it carries all that latent heat up into the atmosphere, and that is exactly what fuels the storm's convection and those massive, destructive winds.
And this builds into a perfect storm through a pretty deadly chain reaction. Warm ocean surfaces evaporate, and that latent heat powers the storm's convection. But right here is where that deep heat completely changes the game. Normally, a really strong storm churns up cooler water from below, which sort of acts like the brakes, slowing down its own intensity. But remember that heat extending 2,000 meters down? Yeah, there's no braking mechanism anymore. Since the upwelling water is just as warm, the result is that these storms are rapidly intensifying over very long distances.
Plus, it's not just the wind we have to worry about, it's the water. A warmer atmosphere holds a lot more moisture. Because of this whole ocean-atmosphere coupling, the extreme rainfall rates in these storms have shot up by about 10 to 11%. So when these things finally hit land, they're carrying a profoundly heavier payload of water, which leads to those much more severe, devastating flooding events.
The bottom line here is that storms are pulling so much heat from these deep reservoirs that they're literally outgrowing our traditional measurement scales. We're seeing storms jump full categories, going from relatively weak to major hurricanes in a terrifyingly short amount of time. In fact, research shows that a lot of recent storms hit intensities a full category higher than they would have in a cooler climate. It's gotten so extreme that scientists are actively debating right now whether we need to add a Category 6 classification just to handle these exceptionally intense, deep heat-driven monsters.
Moving on to part three, surge versus tsunami, understanding the dual threats.
It's super critical we clear up a really common misconception here and distinguish between two lethal coastal threats. On one hand, you have the storm surge. That is an entirely atmospheric event where abnormal water levels are just pushed ashore by extreme cyclone winds and low pressure. On the other hand, a tsunami is purely seismic. It's generated by underwater earthquakes, landslides, or volcanoes. They are fundamentally different mechanisms. Storm surges are directly fueled by our warming ocean engine. Tsunamis are not.
However, they do share a common amplifier. Thanks to the thermal expansion of these warming oceans, because remember, water literally expands as it heats up, we now have higher baseline sea levels globally. And these higher sea levels are allowing both of these devastating phenomena to travel much, much further inland. So whether it's a wind-driven surge or a seismically driven tsunami, a warmer, higher ocean means the damage penetrates way deeper into our coastal communities.
That takes us to part 4, the human and ecological toll, the real cost of a warming engine.
Look, this isn't just theoretical data on a spreadsheet. These intensely amplified rainfall dynamics are turning historically weak storms into massive, unthinkable tragedies. In Southeast Asia, ocean-warmed cyclones recently caused catastrophic flooding and landslides that displaced thousands of people and killed over 1,600 individuals. The extreme social and economic costs of this warming engine, they're being paid in real human lives right now.
And beneath the waves, the impact is just as severe. The ecosystem is desperately struggling to survive in this hot water. We're seeing severe habitat loss, widespread coral bleaching, declining marine biomass, and just crashing biodiversity overall. Marine species are simply failing to adapt fast enough to this warmer, incredibly variable environment. Basically, the ocean is suffering a massive fever, and every living thing inside it is feeling the effects.
Finally, Part 5, Preparing for the Future, Mitigation and Adaptation.
Let's start with mitigation, which is fundamentally about stopping the root cause. The absolute most effective long-term strategy here is rapid decarbonization. We have got to cut off the heat supply to the ocean battery. By reducing greenhouse gas emissions and aggressively transitioning to renewable energy sources, we can slow down the amplification of this extreme weather. We have to stop overcharging the battery.
But because there is already so much heat locked into that upper 2,000 meters of the ocean, we also have to adapt. We have to figure out how to survive the effects that are already locked in and happening right now. This means improving our forecasting technology, strengthening our coastal defenses, enhancing community disaster planning, and, in some high-risk zones, having those really tough conversations about planned retreat policies. Actually moving infrastructure away from the most dangerous coastlines. It all brings to mind this really powerful realization. The world's oceans, which were once this amazing stabilizing force for Earth's climate, are now a key engine of climate-driven disasters. Understanding this transformation isn't just an academic exercise. It's about demanding a complete rethinking of our relationship with the sea and recognizing it for the volatile engine it has become. So I want to leave you with one final, critical question to think about. As our oceans shift from a protective shield to an engine of destruction, will we adapt fast enough to survive the storms we've fueled? It's a heavy question, but one that requires immediate collective action from all of us in this increasingly turbulent world. Thanks so much for joining me for this explainer. Keep asking questions and keep looking at the science.